Hello guys! Today we step into a new age of physics which is known as modern physics. So far we have been studying classicals such as Newtonian mechanics, electricity, and some of the optics that we have seen is also classical. However, starting in the second half of the 19th century, it was noticed that our understanding of the physical laws fails when it comes to small objects such as atoms. If we go into the atom or into the nucleus, we cannot treat matter and objects using the physical laws that we have seen so far. You have seen a glimpse of modern physics when we studied photoelectric effect, the previous chapter. We're gonna start up from here, we're gonna study the atom, we're gonna go later on into the nucleus inside the atom and try to understand and collect some data about the latest ideas related to these subjects. First, let us start with the atom, the particle that took more than 2,500 years to be fully understood. And no, I can't say fully understood. So far, we do not have a complete overview of the atom. Then, after we finish this section, or this chapter in fact, let your imagination guide you for what might come next. Now, here we go. The first idea of the atom was introduced around 2,500 years ago when a Greek philosopher called Democritus suggested that all matter is made up of uncuttable units called atomos, or simply atoms. Each type of matter has its own set of atoms. For example, according to Democritus, iron is made up of tiny atoms having the shapes of hinges. Once they combine together, they produce the solid iron. The idea is very close to what we may understand about atoms. However, it was discarded back then because of another theory which suggested that matter is made up of the four basic elements: earth, water, fire, and wind. It was until around 2,200 years after that when an English chemist called John Dalton reused what Democritus said with a simple update. The twist that Dalton said or used is that atoms are the smallest building structure of matter. That's right, but their shape is almost the same. They are all spherical. Atoms of the same element are identical. Different elements have different atoms. Nevertheless, when these atoms combine together, they can produce compounds. Pretty close to what we know about atoms nowadays. And by the way, with John Dalton in 1805, the history of development or of studying the model of the atom evolved rapidly. Not far after that, not long after that, after around 100 years, another English physicist this time took the idea of Dalton and suggested that the atom is positively charged and it contains embedded inside it small particles called electrons. They are negatively charged. Negative and positive produce zero charge. But the idea that Thomson introduced is that the atom is no longer the smallest building structure of matter. The atom is made up of the positive charge and the electrons. He called his model the plum pudding model because if we use the modern plum pudding, imagine that you have a muffin, a raspberry muffin. The muffin itself is the positive atom, while the raspberries are the electrons, which are negatively charged. That is how Thomson pictured the atom. After around 12 years, an English scientist, in fact he's from New Zealand, but New Zealand and England are within Great Britain. So another scientist called Ernest Rutherford introduced a new model of the atom. After performing an experiment with a gold foil, he noticed that there is a concentration of the positive charge within, which you can see here in red, and he called that the nucleus, which contains protons. Now, negative charges, which Thomson introduced, which are the electrons, rotate or revolve around the nucleus at relatively far distances. That is also closer to what we know nowadays about atoms. A couple of years after that, a Danish scientist called Niels Bohr, inspired by the planetary model, refined what Rutherford said. According to Bohr, the nucleus is inside, just like the sun is, Electrons rotate around the nucleus in well-defined orbit. An electron cannot exist anywhere. It should be on one of the orbits, which he called back then energy levels. That was a very close model, and we're going to study it in this chapter in more details. After 6 or 7 years, a new age of physics started. It is known as the quantum physics, which is a modern part of physics. It is modern physics itself. Now, a lot of scientists contributed in quantum mechanics. On top of these, we have Erwin Schrödinger, the Austrian physicist who suggested that the electron isn't just simply rotating around the nucleus. In fact, you cannot restrain the electron in one position. It keeps on buzzing, thus producing an electron cloud, as you can see on the bottom right. So this model is called the electron cloud model, and I'm pretty sure most of us have heard about it. It is what we understand the atom to be as nowadays. But this is not the end of our story. After 12 years, James Chadwick discovered that the nucleus contains protons and neutrons. So with Chadwick, now we have the three subatomic particles: the nucleon, the neutron, the proton, and the electron. After Chadwick, by around 7 years, Otto Hahn, a German scientist, succeeded at splitting the atom. After 6 years, and based on what Otto Hahn did, the first nuclear bomb was dropped by the US of A onto the Japanese city Hiroshima. The result of this explosion was devastating, the first atomic bomb in history. It caused around 160,000 casualties, and it ended World War II. And here, development was faster. In 1960, an American physicist invented the laser. After around 30 years, in 1990, we couldn't think of any branch of industry that doesn't use lasers. For example, all of you nowadays use your cell phones. All of you used your computers. Computers have CD-ROMs. CD-ROMs read by lasers. We have scaling devices that use lasers. We have cutting devices that use lasers. Printers use lasers. So lasers are found almost everywhere. And the main functioning of a laser is based on the atom itself. In 2000, and in the University of Washington, a group of physicists succeeded at visualizing and producing the first picture of the atom, a real picture of barium ions or atoms. In 2013, a physicist from Netherlands, Stodolna, captured a photo of the hydrogen atom. This was fascinating. Now we are in the year 2020. What comes next? What would the future hold? Let your imagination guide you concerning that. But we're not gonna stop here. We'll move back now to study the atom as we are able to understand it. The model of the atom, which you can see in front of you now, is the most accurate model, is the electron cloud model. However, the mathematics using the electron cloud model is very challenging. We're not gonna consider it. We will stick to what Niels Bohr once said concerning the atom and thinking about the atom. Never express yourself more clearly than you are able to think. According to our knowledge, the best model that can serve and help us understand how things operate without going into complicated ideas is the model produced by Niels Bohr. You can see here in the picture a nucleus containing protons and neutrons, and that's the update that we added to Niels Bohr, with the electrons around the nucleus in the planetary model. Now we'll move on to start our chapter, which is the atom. So first, let's take a look at what is the chapter about, then we'll start striking ideas of this chapter. By the end of this chapter, we need to know that an atom has discrete energy levels. We need to be able to draw the energy levels in general and for hydrogen. And the most important part is differentiating between absorption and emission spectra. Now, in this video, we're gonna discuss three ideas. First, the prerequisites that we might need, Bohr's model of the atom, and his model of the hydrogen atom in specific. After that, we're going to go to absorption and emission. First, let's focus on the main ideas in the development of the atomic model. So first, the whole story started with Democritus. After around 2,200 years, Dalton refined that model. 100 years after that, Thomson introduced the notion of electrons embedded within the atom itself. 10 to 12 years after that, Rutherford suggested that the nucleus is positively charged, containing protons, surrounded by the electrons. Niels Bohr took that point and refined it by suggesting that electrons are found on well-defined orbits, which he called levels. Then, Erwin Schrödinger introduced the modern idea or insight about the atom, in which we have the electron cloud. So these are the basics. Our main concern is Niels Bohr model, which is found here, and you will notice this within the chapter. The second important thing we need to review before we move on is Einstein's model of light, in which Einstein suggested that light is made up of special particles, which he called photons, sharing some properties of particles and waves simultaneously. A photon has zero charge and zero mass. It has wavelength and frequency, and it has energy given by E = h nu. Not any energy, it's a unit energy. How is it a unit energy? Because when a photon interacts with matter, it either gives all its energy or none. We cannot dissect that energy into smaller values. A photon cannot give half of its energy, or 20% or 40%. It either gives all or none. We have to keep that in mind so that when we start studying the atom, we can use it fluently. The main part of the chapter is Bohr's model of the atom. First, this model is known as the planetary model of the atom. According to Niels Bohr, there is a nucleus. The nucleus is surrounded by electrons. Now, before we move on, it's important to keep in mind that Niels Bohr studied the hydrogen atom first. What we're doing here is generalizing the study. So, the planetary model suggests that there is a nucleus and electrons orbit the nucleus on what we define as energy levels. Now, the energetic state of the atom is described by its electron state. In this figure, you can see many electrons. However, again, Bohr's model was based on one electron atom, an atom with one electron. Now, if the atom has more than one electron, you will notice that there is one peripheral electron, one outermost electron. This is what we study first. So, when we say that the atom has this amount of energy, what's meant is that the electron is found in this state, or the electron has this amount of energy. So, when it comes to electrons inside an atom, we can talk about the energy of the electron, meaning the energy of the atom. Keep that in mind. Not only that, an atom has discrete values of energy called levels, and being in an intermediate state is strictly forbidden. This point, we need to stop at this point a bit, because this point plays a major role in what we call this theory as. In fact, we call it Bohr's model. A model is something that has a certain design but lacks the 100% description and explanation of it. According to Niels Bohr, an electron is either found in level here, in this level, level 1 let's say, or in level 2, but it cannot be in between. Now, why? He didn't answer that. It was later on in quantum mechanics that we were able to explain that. However, in Bohr's model, there was no explanation for why can't an electron be in an intermediate step. You can think about it as if, since we are going into the smallest structure of matter, the atom, so we are also studying the smallest step of motion, which is moving from level 1 to level 2. That is a discrete step. We can either be in level 1 or in level 2. Take a minute to think about this. As you are doing this, whenever I explain this part, I always think about a quote that Niels Bohr once said. When it comes to atoms, language can be used only as in poetry. The poet is not nearly so concerned with describing as with creating images. So, a poet doesn't describe facts. A poet simply creates images. So, in this model, Niels Bohr revealed this aspect. And the astonishing thing is that later on, this model was correct. Now, even though Bohr lacked the explanation, but he struck the bullseye, and that was really amazing. So, whenever we study an atom relying on Bohr's model, keep in mind two main ideas. One, while inside the atom, the electron is bounded to the atom. So we say that the electron is bounded to the atom. The energy of this atom or its electron is referred to as negative. Okay? The values of energy as well are discrete. We call them quantized. So energy can either be on level 1 or on level 2, but not in between. And that's very weird. The second point is, when an electron exits or leaves the atom, it is said to be free. Now we know that when an electron leaves an atom, then the atom becomes an ion. Okay? So the energy of, what we need to know here is that the energy of the electron is referred to as positive here, which is kinetic energy half mv square. Thus, it may admit any value. We call that continuous. So these two main ideas are extremely important whenever we need to study atoms relying on Bohr's model. Keep them in mind. The energy of the electron while it's inside the atom is negative and discrete. When the electron leaves the atom, its energy becomes positive and continuous. So, energy being negative, and the electron can occupy definite energy levels. Niels Bohr suggested now an energy level diagram to show the energies of the atom or the electron inside the atom. We take the general case. If you look at the figure, you can see the lowest value of energy, n equals to 1, the first energy level is, okay? Its level is called ground state or fundamental state. Go to n equal to 2, notice n1, n2, the first level, the second level. This level, E2, is referred to as the first excited state. When you are excited, you are agitated, you have excessive energy. Now, usually when you are excited, we shout, we do anything to release that energy and move to the lower energy, which we call our ground state. The same idea holds true here in an atom. The higher we go, the more the energy is. The atom isn't stable. To be in its most stable situation, the electron should occupy the least energy value. Now, we call these values accordingly: ground state, first excited, second excited, or first level, second level, third level, etc. Now, the last energy level, which is referred to here as E infinity, is called ionized state, because as of this state and up, energy is no longer discrete, as we have said. Energy is no longer negative as well. Ionized state, because when the electron leaves the atom becomes an ion. So we call that free electron state or ionized state. Now, a question that I would like to think about. Since the electron can be either in the ground state or in this state, n equal to 2. So an electron is either found here or there. But an electron can move from one level to the other. How does it move? If it moves from here to here, like think about it as if you are shooting a ball from the first floor of your house to the second. The ball moves through the space between the first and the second level. Now, does the electron do this? If it moves across the space, doesn't this defy what Bohr said? An electron cannot be between two states. If that's true, what happens? I'll not answer that. Think about it. An example which was developed later on, not only by Bohr, the mercury atom. You notice the least energy is minus 10.45, and the unit we are using here is the electron volt. You all remember electron volt, the 1.610 minus 19 joules, right? Okay. So, The least energy, which is the ground state of the mercury, is minus 10.45. The first state is minus, or the first excited state is minus 5.56. Now in between there is emptiness, nothing. Levels continue. Now notice here the figure can show 1, 2, 3, 4, 5, 6, 7, 8 levels. When you go to 0 there is some space here. In the case in general we have drawn a couple of states. Why am I saying this? Because when it comes to the infinity state, which I passed quickly first, when it comes to the infinity state, a lot of students ask, what is infinity here? Well, in fact, unlike in mathematics, infinity here is a number such as 9 or 10, because an atom doesn't have infinite values. It has discrete values, 1, 2, 3, 4. The maximum is 8 or 9. You all know the periodic table. So infinity here is tops 12, not more than that. It can't reach 12 as well. Another example is the lithium atom. Notice that energy values are different. Nevertheless, they are also discrete. Look at the discontinuity in values. And they are also negative. Once again, inside the atom, energy is negative to indicate that it's bounded. The electron is bounded to the atom. And energy values are discrete. The electron can either be here or here. Being in between is strictly prohibited, strictly forbidden. Keep that in mind. Now, we said that an electron can either be in level 1 or level 2 or level 3, but cannot be in between. Okay, but an electron is able to move from one level to the other. That's true. How does that happen? We should give it some energy. So if an atom is given the exact amount of energy, it will pass to a higher energy level. I will focus here on the point of exact amount of energy, and I want you to hear carefully what I'm saying. Exact amount. Now, why is it exact? We'll talk about it. So look at this animation. An electron is found somewhere. It's rotating. It receives a photon. This is a photon. The energy of the photon is exactly delta E, the difference between this level and this level. Why exactly? Because if the photon is absorbed, we know that photons are completely absorbed. All energy or none, you can see it here. If that photon's energy is taken, then the electron would move from this state to wherever this value takes it. If this value takes the electron to this level here, in between levels, it doesn't exist. An electron cannot be there. So, as if the atom thinks, if this energy isn't enough to move to a certain level, so it will be discarded. If this energy will move the electron to this level, higher than a certain level, it's also discarded. The energy of the photon must be exactly equal to this. I always think about it as a key opening one lock. So if there is this lock, and in specific, this key. This key opens this lock, and this lock is opened by this key. You cannot use this key for another lock, and you cannot use another key for this lock. I repeat, a photon interacts with an atom when its energy is exactly equal to the difference between two levels, because the atom will absorb all the photon or nothing and will move to a new level. Two conditions must be taken into consideration. The photon's energy is completely given or none, and the electron itself can either be in a level or none. So two cases, two discrete or discontinuous things take place here. That's why you have to pay attention. If we continue the animation, notice the electron absorbed the photon. There is no more photons. The electron vanished at the lower level and appeared in the higher energy level. We can say the electron passed from the first energy level or from a lower energy level to a higher energy level. It moved. We call this the quantum jump because it's a very weird jump. The electron vanishes at a point and reappears on the other. And again, remember what Bohr said. Imagination and create images. Explaining facts here is really very hard, because simply if you ask me, how does that happen? I will tell you, I don't know. It happens. The electron is here, it vanishes, taking that energy, and reappears. I can provoke many other questions. How can the atom know that this is a suitable photon? Many things can be considered here. Really, it's endless. If you try to think about it, it's mind-blowing. But it happens like that. And that's what we need to focus on. This is what happens. We just use it and continue. Later on, anyone who's interested might go into higher order physics and study it. Now, this animation can be represented mathematically such as this. Okay? A photon, we draw the electron in the first level, an arrow, a dotted arrow, to show the higher level. Or, what I prefer is this. A photon arriving at a certain diagram, we draw the lower level, the initial level, as dotted, the upper as a solid electron or circle, and the transition is shown by a dotted line. Energy of the photon which is absorbed equals h nu, and it must equal final energy minus initial energy. Okay? Now, when it comes to final minus initial and initial minus final, that will cause a problem later. So, a piece of advice, always take it E higher, E high, minus E low. Okay? I'll try to write it here, even though it's a bit tricky. E low. Okay? Now, that's how an electron moves from a lower level to a higher level. We say that the photon here is absorbed. So absorption is when a photon is taken so that the electron moves from a level to a higher level. Moving. Now downward transition. The atom or the electron is found in a certain level. That level is a bit higher than the fundamental level. So the electron will eventually move down. We say that a photon is emitted. Now what's the energy of that photon? Simply, it is the difference in energy. So if the atom had minus 5 joules, it moved to minus 6. So it lost 1 joule. So the photon given is the 1 joule energy. Let's check it as a figure. The electron is found in the higher energy level. It vanishes and reappears on the lower level, giving this photon. Right? Now, this photon leaves the atom. You can see it later. And that's how we represent it in a diagram. In a circular diagram, here in the upper right, and using the regular diagram, which I prefer, as I told you before, on the lower right. The initial state here is up, in which we draw the electron dotted. The transition is indicated as a dotted line as well, and solid line showing the final state. And notice that I've drawn the photon, sorry for that, and notice that I've drawn the photon after, as if it's leaving the transition. Energy of the photon, which is preferred to be called photon, not gamma. So it's better to say E of photon, which is emitted, pH, emitted, which equals h nu or hc over lambda, but it equals here E initial minus E final. Notice once again, E high minus E low. So by this, we studied the energy levels as proposed by Bohr. We studied the upward transition in which photons are absorbed, and downward transition in which photons are emitted. Now starting with an application based on Bohr's ideas. Bohr's ideas are all qualitative. We don't have a lot of mathematics there. Okay? Just keep in mind that energy of a photon is always energy high minus energy low. And the atom can either be in a level or not in between. Okay? So it's either being in a level or not. We don't have intermediate stages. So a hypothetical atom or hypothetical energy levels of a certain atom are shown. You notice that E1 is minus 122 electron volt, if you look at the scale used here. The second level is minus 30, third level is minus 13. You can say the ground state, first excited, second excited, and so on. We shine on this atom two photons. The first has an energy of 108.8, the second 112. Definitely electron volts. Which one of these photons is absorbed by the atom according to electronic transition? And why? The atom is now found in the third energy level and it undergoes transition, downward transition to the second level. So the first question is moving up. We call that absorption. The second question is moving down, downward transition. We call that emission. How do we write this when it comes to questions and answers? Let's move on and check. First, you notice in the given we have the basic values given, H, C, and 1 electron volt conversion. So let's move to answering 1, which is simple, by the way. First, I'll just rewrite the question. Two photons are incident on the atom, which is found on this level, or the electron is here. Same thing, the atom or electron are alike. Now, if this photon, the first photon, let's take the 108.8 electron volt. If the photon is absorbed, then this energy minus 122 will have an extra 108.8 added to it, and we'll check the final answer. So I'll do simple mathematics, which is logical. Minus 122 plus 108.8 equals minus 13.6. So the answer, minus 13.6, happens to be equal to E3. Since this key, this photon, the key, matches this lock moving from 1 to 3, then what happens is true absorption. So yes, this photon will be taken, the electron will vanish from here and reappear where? On E3. Again, we took the value of the photon and we added it to the initial energy of the atom, minus 122. The final result is minus 13.6 electron volt, which happens to be E3. Now, the electron will take that energy, or the atom will take that photon, and it will reappear on the level E3. I will not talk about what happens from E1 to E3. Just forget about it for the time being. Now, we say that this photon is absorbed. Notice the vocab. And the atom is excited because it takes excessive energy to level E3. Taking the second photon, 112 electron volt, which is more than 108.8. So one might think that the electron will move here, maybe, right? Same technique. The energy is minus 10.4. Now, is there any minus 10.4 here? Minus 10.4 is between these two values. So the electron should be somewhere over here. Can it? Can it happen? Can the atom or the electron be in an intermediate stage? According to Bohr's mole, this is strictly forbidden. So nothing will happen. Nothing energetically will happen, to be more specific. Therefore, I can deduce now that this photon is not absorbed because the atom cannot exist in an intermediate stage. At this point, try to repeat this and focus on the terms used. Okay? Now moving on to the second part of the question. First, writing the question itself. The atom is now found in the third level and it moves downward transition, notice the term, downward transition, to the second level. The best thing to be done here is draw a figure. Now, if you want to stick to this figure, why not? E3, E2. Okay? So, downward transition, then the energy of the photon which is emitted equals E initial minus E final, because you are moving from higher to lower, right? Now, look at the figure. E3, E2. I can write E initial, E final. Dotted electron, solid electron, and a line in between. One might argue, why is the electron drawn solid here? It's okay. It's not the end of the world. And the photon is emitted. Now calculations. Energy of the photon. Since the question demands frequency, so I'll rewrite this equation using energy of the photon as h nu. E3 minus E2, because this is the initial and the final. Keep in mind, we always go towards initial and higher energy minus lower energy. Now, H is given. E3 is given minus 13.6 electron volt. and E2 is given minus 30.6 electron volt. So just replace. Okay? Now, electron volt isn't accepted as a unit, especially since H is in joules times second. So we'll convert the energy value to joules, and that's what you can see here. Continuing with simple mathematics, frequency equals 4.8 times 10 to the power 15 hertz. So this is a problem about absorption and emission without taking any mathematical equation. By just using logic, we are able to answer it. This is the first part. I hope that you didn't find it hard. Now, we'll just move on to study the hydrogen atom quickly. Section 17.3, Bohr's model of the hydrogen atom. In fact, this is the most important part of the chapter because Niels Bohr performed his study on the hydrogen atom at the beginning. Then we generalized the whole theory or the whole model. So, when he did the calculations, Niels Bohr reached the result or the conclusion that the energy of the hydrogen atom described by the state of its electron is given by the equation minus E0 or 13.6 electron volt over n squared, where n is 1, 2, 3, etc. Now, when you look at this equation, many terms catch our eyes. First, minus. Why is En negative? Simply, we are describing the electron inside the atom. And we said, according to Bohr's model, energy is negative to indicate that the electron is bounded to the atom. N being 1, 2, 3, 4, etc. If you replace n by 1, you get a value. If you replace n by 2, you get another value. And in between, there is a huge gap which has no values in between. This proves that energy is discrete and not. So, minus indicates that the electron is bounded to the atom. N, or n squared, indicates that values of energy will not form a continuum or continuous values. They are discrete. The 13.6 electron volt, it's a value derived from using some classical calculations of kinetic energy and electrostatic energy. We are not going to go there. In fact, the whole equation isn't important for us as students. If you look at the model, the circular model proposed by Bohr, you can see that we have a proton, which is the nucleus, surrounded by different energy levels. Now, these energy levels, n equal to 1, 2, 3, etc., are energies or levels occupied by the electron, and nothing in between. Now, let's try to draw the energy level diagram of hydrogen. Based on the equation minus 13.6 electron volt over n squared, we'll take different values of n and check the result. For that, we'll have the energy axis, as you can see on the right hand side, labeled in electron volt. We start with n equal to 1, which we defined previously to be the ground state. Its energy is minus 13.6 electron volt. Now, as n will increase, this value will decrease. Therefore, this is the least energy level. We call it fundamental state or ground state. N equals to 2 is the second energy level, or the first excited state. Calculations give that the value is minus 3.4. Now, this is the point. Minus 13.6 minus 3.4. There is a 10.2 energy, electron volt energy in between. That's completely nothing. It has nothing in between. An electron cannot be in between these values. An electron can either be in the ground state or in the first excited state. When it moves from here to there, it vanishes and reappears. If you want to call it magic, call it. If you want to read about it, feel free to go and read. If you go to n equal 3, third energy level or the second excited state, energy is minus 1.51. Notice that the gap decreases. N equals to infinity, we call the ionized state. Notice these other values, they get closer to each other. So the closer we get to 0, the less evident the discreteness of values that appears. And don't forget, above ionized state, energy is continuous because it's kinetic, half mv squared. Now, we go to an application on the hydrogen atom specifically. Notice this is, by the way, extracted from an official exam. the energy of a hydrogen atom in electron volt is given by En minus 13.6 n squared. n belonging to n star, that is, natural number not being 0. Values of C, H, and electron volt conversion are all given. Let's read the questions together. Again, this is an official exam. Calculate the value of the maximum energy of the hydrogen, the minimum energy, energy of the first excited, energy of the second excited. A question which is purely vocabulary. Deduce that the energy of the atom is quantized. Calculate the frequency of the radiation needed by a hydrogen atom found in the ground state to pass to the second excited state. Question 2, deduce that energy is quantized, introduces the term quantized, which I have used verbally a lot. Now we're going to write it. So starting with the solution, part 1, we are supposed to find energy in different levels. Now I will scroll the answers, but before that, if you look at this equation here, as n increases, energy decreases. But since it is being negative, when the value decreases, it approaches 0. Therefore, when n increases, En increases too. Why? Because it is in the denominator and it is negative. That is, the maximum energy of hydrogen corresponds to n equal infinity or tends to infinity. Now here I used two things. First, I analyzed using mathematics. Second, I still remember what we have talked about. So memorizing some terms here will make answering questions much easier. So energy maximum of the atom is 0. When energy becomes more than 0, we no longer have hydrogen atom. It becomes a hydrogen ion. We call that ionized state, if you remember. Minimum energy is when n equal to 1 because n cannot be 0, replacing minus 13.6. First excited state is when n equal to 2 and do the math. Second excited, n equal to 3 and do the math. You notice that the questions are straightforward, nothing that we have to think about, not even the equation. Deduce that energy is quantized. We said before that the term quantized means discrete values, non-continuous or whatever. Here is a written answer. Since energy admits discrete or specific values and not continuous ones, we say energy is quantized. Section 3. Calculate the energy of the radiation needed by hydrogen found in ground state to pass to the second excited state. So we are in the ground state to move to the second state. Now that is an upward transition. It is good if you draw a figure showing dotted at the lower level and a solid electron on the higher level. But in fact, bottom line is that this is an upward transition. So moving from 1 to 3 is an upward transition. Now why n equals 3? Because it's the second excited. So a photon is absorbed. Using Bohr's model, when a photon is absorbed, we write E photon absorbed equals h nu, which is hc over lambda, which is E final minus E initial, E high minus E low. Now I always write the energy of the photon as both h nu and hc over lambda. The question here demands frequency, so I could have dropped the hc over lambda. Continuing with values, don't forget that E final is E3, E initial is E1. H nu equals E3 minus E1. The values E3 and E1 are calculated in part 1, so I replace them. So H nu equals, here is a typo, this should be plus. Okay, because minus and minus become plus. Converting to electron volt and doing the math, nu equals 2.2992 times 10 to the power 15 Hertz. So you can check this problem again. It's easy. It doesn't have a lot of things to think about. However, the problem here is using values, using numbers. It is usually tricky. Notice this simple mistake that I've done here by converting the minus to plus or the plus to minus might lead to catastrophes. So pay attention when you replace values. In this, be neat as much as possible, and all exercises will be simple. Now by this, we finish this section. I won't write any summary because the chapter has no summary. It has all like just ideas that you need to go over. I will suggest one exercise which is a bit tricky and hard. You can also solve number 11, page 299 from the book. Now in this exercise we have some complicated stuff. You might face problems in parts 1 and 2. However, 3, 4, 5 shouldn't be hard. Solve them please. Next time we meet, at the beginning of the video I will post the answer of this. Then we continue with the remaining part of the chapter. I think that it was a bit hard. The chapter is a little bit new. It contains many ideas that you are not familiar with. However, we need to crack it. So go over the video again, please. If you want, you can write a simple summary to make sure that all ideas are grasped properly. Until we meet another time, take good care of yourselves and see you later.